When we talk about probability, most people think of this as gambling or frequency. The idea that if we flip a coin infinite times, 50% of them will be heads. But in artificial intelligence, we don't care about flipping coins. When a self-driving car sees a shadow on the road, it can't replay the scenario a million times to see if it crashes. It has to make a decision now based on incomplete information. In machine learning, probability isn't about the frequency of events. It is a calculus of belief. It is a way to quantify how confident the machine is in its own view of the world. Welcome to Decoding Complexities. I'm Pradeep. We have mastered the geometry of data. Now we will master the logic of uncertainty. Today, we start with the building block of everything, the random variable. First, we need to shift our mindset. In classical statistics, data is random, but the truth is fixed. In machine learning, we flip this. The data is fixed. We have the dataset. It's not changing. The truth is uncertain. Our model parameters are the random variables. We use probability to represent our state of knowledge. Probability of 1 means we are certain. Probability 0 means it's impossible. Everything in between is a measure of uncertainty. To encode this uncertainty, mathematically we use the random variable. The name random variable is terrible. It's neither random nor it's a variable in the algebraic sense. A random variable, usually denoted by a capital letter X, is actually a function. It is a function that maps a real-world outcome to a number. There are two different types of random variables. The first one is the discrete random variables, which maps to a specific integers, and the second one is the continuous random variables, which maps to any real number. In linear algebra, our atom was the vector. In probability, our atom is the random variable. We don't operate on numbers anymore. We operate on these distributions. So, how do we describe X? Since it represents uncertainty, it doesn't have a single value. It has a distribution. For discrete variables, we have a probability mass function. It's a list of probabilities that sum to 1. For continuous variables, we have a probability density function. This describes the shape of the probability. The height of this curve tells us the likelihood of a specific value. The width tells us our uncertainty. A narrow, tall curve means the AI is confident. A wide, flat curve means the AI is confused. Learning, in a nutshell, is just the process of taking a wide, flat distribution and squeezing it until it peaks over the correct answer. Let's make this concrete. We don't just write these on paper. We simulate them in Python using NumPy and SciPy. We will generate a continuous random variable representing the height of adults. We assume it follows a normal distribution. We define the mean, our best guess, and the standard deviation, our uncertainty, then we sample from it. Let's visualize this belief. This plot is the fingerprint of the random variable. If we increase the sigma, that is uncertainty, to 50, look what happens. The curve flattens. The AI is less sure. In machine learning, our goal is to minimize this spread. So, we have redefined our world. We moved from deterministic vectors to probabilistic distributions. We learned that probability is a measure of belief, and the random variable is how we encode that belief in code. But in the code, I just assumed the data followed a normal distribution, a bell curve. Why? Why do we assume the world is a bell curve? Why not a triangle? Why not a flat line? It turns out there is a profound mathematical law that forces nature to form bell curves. It is called the central limit theorem, and it is the reason behind linear regression. This is the topic of our next video. Link for the companion blog post and the collab notebook is in the description. Hit that like button and subscribe as we continue to decode the logic of uncertainty. Thank you for watching, and I will see you in the next one.